Welcome back. Where we left off, we were looking at general solutions to trigonometric equations, right? Finding solutions to sine of something equals number. And that's a good start, but it's not going to be enough because there's a lot more trigonometric equations out there. So let's see, that's where we ended up. We had these general cases. We had, if you had arcsine involved, you got a solution. It's probably going to be the case that you're going to have theta plus 2k pi and then maybe negative theta plus pi plus 2k pi, which you can kind of rewrite in this fashion. If you use arc cosine, then because cosine is even, you had theta plus 2k pi, again, and then negative theta plus 2k pi. And if you use arc tangent, well, you had theta plus 2k pi, I guess, and then theta plus pi plus 2k pi, and that's because tangent was periodic with period pi, and that got us all of our solutions. So we will be using that going forward. Hold on to this, it's going to come up for pretty much the rest of this unit, or at least until we get to alternate coordinate systems there towards the end. These are facts that we just got to hold on to. I digress. It's not going to be enough. Let me show you what I mean. Right, arc sine and arc cosine and arc tangent are great. They are inverse functions. They undo sine, cosine, and tangent respectively, but that's all they undo. Right, arc sine undoes sine. It does not undo 2 sine of x. It does not undo sine squared of x. It does not undo anything but sine of x. And so, when we are trying to work trigonometric equations, and we don't simply have sine x equals number, or cosine x equals number, or tangent x equals number, we have to work to get there first. Right, here's an equation, 2 sine x plus 1 equal to 0. I simply cannot, right now, take the arcsine of both sides. Right, the arcsine does not distribute in the same way that sine does not distribute. It is not a multiplicative function. And so we have to solve first for sine, the unknown function type, right? Solve for the thing x is trapped inside, and then solve for x using arcsine. So that's going to be our strategy here. We're first going to solve for the equation, or the unknown identity, call it what you will, and then we will solve for the actual unknown x. So here, we're going to solve for sine x. We're going to do that using just straight algebra. Subtract the 1 from both sides, divide by 2, and we end up with this equation, which is equal to the previous, right? It's equivalent, and that is sine x equals to negative 1/2. Now, this is something I can take the arcsine of to both sides and get my solutions. Right? The unique solution that arcsine of negative 1/2 will give me is negative pi over 6. Right? That's the value between negative pi over 2 and positive pi over 2 that satisfies the condition that sine of that angle is negative 1/2. Welcome back to inverse trig. And the other unique solution, the other non-coterminal solution, is going to be the supplement of that, or 7 pi over 6, which again we get by pi minus negative pi over 6. So that's 7 pi over 6. And I guess that's not truly the supplement, deal with it. That's the same idea though, pi minus angle. And so our solutions then, in general, is the negative pi over 6 plus 2k pi, which again convention dictates we write as 11 pi over 6 plus 2k pi. And the other half, is the 7 pi over 6 plus 2k pi. And that all together gives us all of our solutions, all infinitely many of them. And we can check this. We can check our solutions by putting 7 pi over 6 plus any incarnation of 2k pi you want in there. Take the sine of that, and you should get negative 1/2 there. Multiply that by 2, add the 1, you do get equality. You do get satisfaction. You do satisfy the equation. And also the same if you try negative pi over 6 and anything coterminal with that. And once again, you don't have to write it this way. You could, if you chose, write it as everything coterminal with 7 pi over 6 and 11 pi over 6. That means the same thing. This is just a symbolic way of representing everything coterminal with those two angles. And that means the same thing, that's just as well. But I hope you see the strategy here. Solve for the trigonometric function, and then use inverse trigonometry to solve for the value inside. So here's another one. Find all the solutions to secant of x equals a half. Now once again, I can't just do arc secant. I don't really know what that means. I guess I could if I knew what that meant. That's 1 over cosine. But once again, I can't do the arc cosine of this equation such as it's written now. Arc cosine can only undo cosine. It can't undo 1 over cosine. It can't undo cosine squared. It can't do cosine to the negative first. Arc cosine can only undo cosine. So I need to multiply both sides by cosine, divide both sides by 2, and I end up with a statement 1/2 equals cosine x. Now that I can solve for x using arc cosine. I get x equals arc cosine of a half. I get one solution from arc cosine, and that is pi over 3, or 60 degrees. Cosine's even, so I get the other solution to be negative pi over 3, or negative 60 degrees. And that's my two unique solutions. That together gives me all my solutions at x equaling pi over 3 plus 2k pi, and also, by tradition, 5 pi over 3 plus 2k pi. So hopefully you're seeing the general strategy here. Solve for the unknown identity, solve for the unknown trigonometric function, and then use inverse trig to solve for the unknown inside. All right, well and good. But what about if I had something like this? What if I had more than one trigonometric function going on? What if I had 4/3 cosine theta sine theta plus 3 cosine theta equaling to 0? Now, some of you might be chomping at the bit and say, oh, well, this is 2 sine 2 theta. And you'd be right, but I don't think that's the direction we want to go here. We're wanting to solve this equation, and that substitution might have gained us ground if this had been maybe sine 2 theta over here as well. But as it is, the strategy I'm proposing is instead of doing that, we look at factoring. If I factor out the cosine, which I can do, because cosine of theta is a thing that is being multiplied, right? Cosine itself is not a multiplicative function, but cosine theta, that is multiplied, that is still going to satisfy the commutative property of multiplication. Not the distributive, but the commutative property. And so we can factor that out. And so I've got cosine theta being multiplied onto 4 sine theta plus 3. And all that equals 0. And now we're back in algebra. I've got two things multiplying together to be 0. That can only be true when either factor is 0. And so the solutions to this overall equation comes from either cosine of theta equaling 0, which happens in two places, or when sine of theta, well, because not sine, but 4 sine of theta plus 3 equals 0, right? When this other factor goes to 0. So we have one set of solutions. Pi over 2 plus 2k pi and negative pi over 2 plus 2k pi, which you could actually shorten to just be pi over 2 plus k pi. And the other set of solutions come by taking the arc sine of negative 3/4, right? Because you solve for the sine, and then you solve for theta by doing arc sine. And you get one specific solution from that, negative 0.848. And the other solution is going to be pi minus that, which is going to get us 3.99. And so all our solutions together is written here. Negative 8.848 plus 2k pi, negative whatever that thing was, plus 2k pi, and pi over 2 plus k pi. And that's all the solutions to our equation here. And that's how we can do it, right? We can use algebra now, and we can use all of algebra now, right? We can solve for unknowns and then do inverse trig. We can factor and then do inverse trig on the individual factors, assuming, of course, it's equal to 0. We can do the quadratic formula, even. Suppose I'm trying to find the solutions to tangent squared of x plus 4 tangent of x plus 3 equal to 0. That is an unknown squared plus 4 times an unknown plus 3 equal to 0. I could use the quadratic formula here, but I could also just factor. Right? I can have two things multiplying to 3, adding to 1, pure algebra. That becomes, this expression becomes unknown plus 1 times unknown plus 3. And tangent of x equal plus 1 is true whenever tangent of x is equal to negative 1, which happens at negative pi over 4 if you were to do inverse trig. Arc tangent of negative 1 is negative pi over 4. And you add k pi to that, and you get one set of the solutions. The set satisfying this first factor equaling 0. The other one we can get, again, with inverse trig. Tangent of x equaling -3, arctangent of -3. Not a nice thing, but still a thing. It's negative 1.249. You add k pi to that, we now have all the solutions to this equation. So I said all that so I could say this. All of the algebra techniques you are familiar with, all the algebra techniques you know up to this point, and then some, I guess, all algebra can be used to solve trigonometric equations. In fact, that is the prerequisite to get to where you can just do arc sine or arc cosine or arctangent to find your general solutions. So that's what we're going to be doing here. Our next class, we are going to look at using algebra to get to where we can do the trig to get to the general solutions. So I'm very excited for this part. This is where we get to bring everything together. It's a very exciting time. So I look forward to seeing you in our next class. Let me know what has you the most concerned. Maybe the most disparaging algebra technique for you. What is some algebra technique or some factoring technique you feel you need practice doing in this context? So let me know, and I will see you in our next class. Have a good one.